Good day, ladies and gentlemen. So I'm going to present you my article. Up. So I'm going to try to be quite fast. So the title of the presentation is The Potential of Spineless Cactus as a Drought-Tolerant Energy Crop for Biogas Production, but with like a geographical analysis of the potential impact depending on water use efficiency and the mean annual rainfall that we receive in South Africa. So myself, I'm Axel Tarrisse, and the co-authors are Mrs. Marina de Wit and Johan van Niekerk. So to start with our presentation, we have a table of the biogas yield from Opuntia, where we have 5 different analyses from different types of cactus, different varieties, but all from the same species of Opuntia ficus indica inermis. And as you can see, there are the volatile solids, the methane content of the gas, the CO2 content of the gas, the yield per ton of volatile solids, the yield, the different types of yields, the yields as well in of cubic meter of methane per ton of dry matter, the yield of methane in kilograms of methane per ton of dry matter, the yield of CO2, because biogas is a mixture, is produced from the anaerobic digestion of organic matter by anaerobic bacteria. So the biogas generated usually has 50 to 70% methane gas, and the rest is CO2, and with some traces and so on. But so here we have the different concentration of the gas, and we have the yield in methane and in CO2 with different variables here. And I included also the energy value of the gas generated, the kilogram of gas obtained per ton of dry matter here, CO2 plus methane, which goes from 300 up to 600 kilogram per ton of dry matter, and the energy value of that gas in kilowatt hour of lower heating value and megajoule of lower heating value per ton of dry matter, and as well as the methane in terms of liter of diesel equivalent per ton of dry matter, so that we have an idea of how many liters of diesel equivalent energy can be produced in the form of methane per ton of dry matter. And we can see here that it ranged from 191 liter of diesel up to close to 300 liters of diesel per ton of dry matter. The biogas yield from Opuntia, we have some graphics. It's a plant which is quite ideal for biogas production. Why? Because we estimate from other models, okay, it's not the subject of the presentation, but it's a plant when it's properly managed, properly fertilized, it's very easily digestible. It has a lot of easily digestible sugars. It's very water use efficient. It can yield a lot of dry matter. It can grow in areas that are semi-arid where no other crop can grow as efficiently. And the biomass is extremely easily degradable. Secondly, it has another asset. It has a lot of calcium. It has close to 5 to 10% of calcium in the dry matter, so a lot of ash. And when the gas is generated, the bubbles of biogas, the CO2 in that gas reacts with the calcium and create calcium carbonate, so we obtain richer methane content in our gas. The mean annual, so I'm going to pass into a geographical analysis of the potential in South Africa. So we have included a table of the different classes, of mean annual rainfall in South Africa that range from zero, let's say, less than 50 millimeters up to above 2,500 millimeters of rainfall. We have this range, 150 to 500 millimeters, the surface area represented in the country, what it represents in percentage of the land mass of South Africa, the cumulative square kilometers, and the mean annual rainfall of each classes, and what it represents more or less in million cubic meter of rainfall per annum. Basically, all the tables are a little bit like a guide for the decision maker and for different people that are, wondering what is the potential, what is the energy potential of Cactus? So the most efficient water use efficiency, basically the water use efficiency is how many, we have 1 kilogram of dry matter of Cactus that we produce, how many liters of rainfall does it require to be produced? The very, very efficient, high density, intensively managed cactus plantations in Northeast Brazil, and even in South Africa, we did some preliminary trials, which indicates that we could potentially go as low as 60 liters of water, so 60 liters of water for 1 kilogram of dry matter produced. But in this table, to be more reasonable in our projections, we took from 80 liters of water to 100, to 120, and to 160 liters to produce 1 kilogram of dry matter. Obviously, the water use efficiency of the plant depend on how much nutrient is in the soil, the quality of the soil, the climate, the rainfall, the management, what kind of fertilization is being made to the plant, the density, basically all what is linked to the proper management of a cactus plantation. If it's properly weeded, what kind of variety of cactus is planted, how they are performing on that land. But by having a table that is between 80 liters to 160 liters of water for 1 kilogram of dry matter produced, we know that we have quite we have an efficient, realistic range of what intensively managed cactus can yield in different areas of the world. Can it be in South Africa or elsewhere where cactus can perform properly? And we have on the vertical table a range from 250 millimeters of rainfall to 600 millimeters of rainfall. And this gives us basically a range of 16 tons up to 75 tons. There are certain trials where we can reach close to 80 tons of dry matter, which is the biological maximum of this plant per hectare per year. Basically, we did a correlation, basically an equation which multiplies that basic dry matter yield to the methane yields. So the methane yield in this table varies from 2,600 kilogram of methane to 12,800 kilogram of methane that can be generated in the semi-arid climate range of South Africa. If we take, let's say, a 400 millimeter rainfall area, that kind of climate can yield between 4,000 kilograms to 8,500 kilograms of methane, which is much higher than the highest performing energy crop, which is palm oil planted in tropical rainfall forest, which gives us around 5,000 to 6,000 liters of palm oil. But basically, when we tell a kilogram of methane many people are not really familiar with how much energy it represents. And here we have that same data presented in liters of diesel fuel equivalent. So basically on the same range, 400 millimeter of rainfall, we are between 6,000 to 12,000 liters of diesel equivalent energy in the form of methane generated per hectare per year, which is quite, it's even in the 400 millimeter rainfall area, we have a higher energy yield than the best performing energy crop in the world. While here we're basically creating that kind of value in semi-arid landscape, and we can produce that biomass, the cactus biomass, for extremely reasonable cost, which wasn't included in this article. We did another question to evaluate how many tons of CO2 is captured by the cactus during this intensive and effective growth. And we have between 23 tons to 108 tons of CO2 that can be captured by the cactus each year. As it's a CAM plant, it's extremely water use efficient, and it's much more effective in capturing CO2 because we're transforming land that has very little capacity for photosynthesis to be able to capture 10 times more CO2 per unit of land and with the same rainfall than other type of vegetation or crops or pastures in this rainfall climate gradient, rainfall range. And so it's much more basically effective in capturing CO2 and planting trees or forest in places of high rainfall where anyway the natural climate is forest. And here we have a last table, which basically gives us a range of what is our CO2 gas yield per hectare per year from the anaerobic digestion of cactus. Why is this important? Because CO2 is also a building block. So we have a fantastic plant. It absorbs a lot of CO2. It's easily digestible. It's transformed by bacteria, anaerobic bacteria, into methane and CO2. We have this captured. So we don't need to get a big, complicated machinery to capture the CO2. The cactus does it for us. We have the anaerobic digester, which is basically mimicking the stomach of a cow. Release that methane and CO2. We can take that CO2 and we can use it for any different types of industries, replacing basically fossil-based CO2 for soda drinks, for different types of industry that uses CO2 for welding or for the production of bioplastics or different types of bio-industries. So it's or even for the production of synthetic fuels, synthetic aviation fuels with the Fischer-Tropsch technology. So I thought that it was really important also to give a guidance in how much CO2 can we capture in the form of gas on top of our methane to be able to supply industries and potentially South African industries, which are at the cutting edge of its capacity in Fischer-Tropsch technology to provide feedstock of renewable methane and renewable captured CO2 to these industries to make them greener. And we can see that even we can generate 5 tons to 4 tons of CO2 in the form of gas that can be directed to industries to produce usable products for by human beings. So I don't have much time, so I'm going to try to come to the conclusion. the conclusion is that South Africa has 50% of its land mass that is between 150 to 500 millimeters of annual rainfall. And it has a large amplitude of variation, which makes it difficult to grow conventional crops on it. And this land mass represents 600,000 square kilometers, which is bigger than a country like France. But it still receives 190 billion cubic meter of rainfall per annum. So what could we do to turn that land mass that is extensively used for sheep pastures, of livestock, extensive livestock operations? We can basically, it can be managed with a high potential perennial crop with intensive management. Intensive management doesn't mean really intensive inputs and chemicals and so on. We can manage these plantations in a very sustainable way without basically disrupting the biodiversity, and with maintaining quite a lot of animals, mammals, birds, and insect species on that land, because we have a lot of food and we have a lot of stored water that enables animals like rabbit or ground squirrels and so on to basically develop in this kind of land and provide a source of food for the food chain. So it can also sustain wildlife. And we basically can produce, it's one of the most water use efficient plant in capturing also CO2, as we said, with 80 to 160 liters of rainfall, produce 1 kilogram of dry matter. And 1 kilogram of dry matter of cactus is 1.44 kilogram of CO2 approximately. So not only it's not only water use efficient, but it's highly productive, because we can get 16 to 31 tons of dry matter with only 250 millimeters of rainfall, and up to an outstanding yield of 38 to 70 tons of dry matter with a mean annual rainfall of 600 millimeters. So basically combining intensively managed cactus with anaerobic digestion enable us to pop up the potential of spineless cactus, which can yield, yes, close to 2.5 to 13 tons of methane per hectare per year, approximately, as well as CO2 gas from 5 to 24 tons of CO2 gas in the form of gas per hectare per year, for mean annual rainfall of 250 to 600 millimeters, which could basically enable us to transform this semi-arid landscape into a biosphere vegetative cover, generate a lot of employment of different types of jobs, and ensure proper feedstock for the bioindustries of the future. And I hope that these tables and this article will help people as a guideline, and that we can validate these numbers with coming research. I thank you very much, and I added my personal email address to the contact. Thank you very much for your attention.